Now let's derive the mathematical expression for the intensity of two waves that interact. So in the previous video, we saw that the intensity is equal to constant times the modulus squared of the amplitude function. And I want to emphasize that this expression, alpha times the modulus squared of psi, comes from the idea that we're measuring the energy, the average energy over many cycles of the wave. And that is why we take the modulus of the amplitude squared. I'm going to be a physicist here and I'm going to neglect the constant over here. And why do I do that? It's because I'm only interested in the form of the mathematical expression. I'm not trying to compute certain values or anything. We're only interested in the general description of the intensity of the sum of two waves. The first thing we're going to do is determine the intensity of each wave. So the intensity I1 of psi1 is, well, the modulus squared of psi1, since we're neglecting the constant. But the modulus squared of psi1 is just the modulus squared of the maximum amplitude, the complex maximum amplitude squared. And the reason for that is because the complex exponential never impacts the value of the modulus. Because remember that the complex exponential gives the argument of the complex number. I want you to visualize what I mean by that. The complex exponential gives the argument and therefore the angle of our complex number. But the angle doesn't have an impact on the length associated with the vector of the complex number. And therefore, the modulus and the argument are two different concepts. In essence, we could have this a different argument, theta prime, but still have the same modulus. And in general, the modulus of r e to the I theta, where r is a positive real number, is just r. The modulus is just the factor of the e to the I theta. But the problem here is that a1 tilde is also a complex number. So the modulus can't be a1 tilde because it's a complex number and we want a real positive number. But remember that a tilde, well, a1 tilde is just a1, or a1 is a real number, times e to the I phi. And therefore the modulus of a1 tilde is just, well, the absolute value of a1. The reason why I put an absolute value here is because a1 might be a negative number, but the modulus is always positive. So a1 is a real number. But in this case, since we're taking the square of the modulus, we don't need to put the absolute value sign here. So the modulus squared of a1 tilde is just a1 squared. And a1 squared is a positive number, of course. Likewise, the intensity of psi2 is just a2 squared. Now, our goal is to determine the intensity of the sum of the two waves. So, if we call the sum of the two waves psi, well, the intensity, the total intensity, is the modulus squared of psi. And therefore, the modulus squared of psi1 plus psi2. But one interesting property of the modulus squared of a complex number is that it is equal to the product of that complex number and its conjugate. Therefore, the modulus squared of psi1 plus psi2 is actually just psi1 plus psi2 times the conjugate of this whole complex number, which is just psi1 bar, psi1 plus psi2 bar, where I'll use the bar notation to specify that it's the complex conjugate. You might see other people use the star notation to show that it's the conjugate, but I prefer the bar notation. Now, the conjugate of the sum of two complex numbers is just the sum of the conjugates, And therefore we have psi1 bar plus psi2 bar. Distributing the product gives this expression over here. But we know that psi1 times its conjugate, well, that's just the modulus squared of psi1. As we have seen initially, when we took the modulus squared, and we noted that taking the modulus squared is the same thing as the product of the two conjugate terms. And so we do the same thing here. Here we have the product of psi1 times its conjugate. Similarly, we get the same thing over here. So we have the modulus squared of psi2. Now all is left to do is determine the expression of this sum over here. If you've seen my video on the proof of the triangle inequality, you would recognize what this sum is. This is actually the sum of a complex number and its conjugate. And let me show you why. What is the conjugate of psi1 times psi2 bar? So what is the conjugate? So I'm using the bar notation. So we want to know the conjugate of this product over here. Well, the conjugate of the product is the product of the conjugates. So the conjugate of this product is just the conjugate of psi1, so psi1 bar, times the conjugate of psi2 bar. So we have 2 bars over here. And the conjugate of the conjugate is just the complex number itself. So we have psi1 bar times psi2. But this expression is exactly this expression we have here. In other words, we can rewrite our expression as psi1 times psi2 bar plus bar of psi1 times psi2 bar. But whenever we have the sum of two conjugate terms, so for example z and z bar, well, that's just equal to twice the real part of our complex number. And in order to prove it to you, let's write z in its algebraic form. So z is equal to a plus ib, and z bar is equal to, well, it's the conjugate, so a minus ib. And so when we add z and z bar, we get twice of a. But a is the real part of z, and there we have it. And therefore our expression turns into this, where we have replaced this sum by twice the real number of our complex number, so the product of psi1 and psi2 bar. But one thing you have to remember is that the modulus squared of psi1 is just I1, so the intensity of our first wave. And the same thing for the second wave. So we have I1 plus I2 plus this term, twice the real part of psi1 times the conjugate of psi2. In order to determine this expression, let's evaluate the product of psi1 and psi2 bar. So this is equal to a1 tilde e to the I kx1 minus omega t times a2 tilde e to the I kx2 minus omega t, except that we're taking the conjugate of psi2, so we have a minus sign in the exponential, because effectively taking the conjugate is taking the negative of the argument of our complex number. We can simplify this expression by noting that we have a e to the I times minus omega t times e to the minus I of minus omega t. So these cancel out, so it equals to 1. And we remember that a tilde is a complex number, and it's equal to a, which is a real number, times e to the I phi. And so we have a1 e to the I phi 1. Remember, the phase offset of the two waves can be different. So a1 e to the I phi 1 times a2 e to the I phi 2 times e to the I kx, well, k times x1 minus x2. Unfortunately, I've made a slight error. I forgot to take the conjugate of a2 tilde, because remember, we're taking the conjugate of psi2. And so we need to take the conjugate of this whole expression. So even though I have reversed the argument, I forgot to take the complex conjugate of a2 tilde, because remember that a2 tilde is a complex number. So let me show this. So we have the complex conjugate of a2 tilde. And so we have a2 tilde bar. And a2 tilde bar is manifested by the fact that we have a negative in the argument over here. And therefore we get e to the, well, a1 times a2 e to the I. Phi1 minus phi2 plus k x1 minus x2. And now the real part of this whole expression, well, it's just a1, a2 times cosine of the argument. So delta phi plus k delta x. And therefore we get I1 plus I2 plus twice the A1 times A2 cosine of phi1 minus phi2 plus k x1 minus x2. But remember that a1 is just the square root of I1, and the same applies for I2. And so we get this expression over here, which is actually the mathematical expression that describes the way intensities add up. So this equation describes the intensity of the sum of two waves. And we can clearly see that the intensity of the two waves is not the sum of the intensity of each wave. So I is not equal to I1 plus I2, because we have this extra term over here, which can be either positive or negative. Indeed, cosine can take values that range between -1 and 1. And whenever we talk about the way waves interact in terms of their intensities, we talk about interference. And in order to illustrate this notion of interference, let's take the example of when the two waves have identical intensities. So when I1 is equal to I2, well, then we get that I is equal to twice I1 plus 2 times, well, we get an I1 times I1, which is I1 squared. So twice I1 times the cosine. And let's say that this argument, well, the input is made in such a way that cosine becomes -1, so it has its minimum value. Well, we get I is equal to twice I1 minus 2I1, which is 0. And this case represents destructive interference. So the intensities of the waves interact in a destructive way, in such a way that they cancel each other out. Conversely, if the cosine takes its maximum value, we get that I is equal to 4 times I1. So in this case, we talk about constructive interference. And therefore, this entire term over here underpins the physical phenomenon of interference. But what's even more interesting is not how the intensities don't add up, but why they don't add up. Well, it comes from the argument over here, and so the phase difference. So the input of the cosine is called the phase difference. And phase difference is what underpins interference. But how do we get phase difference? Well, we can get it in multiple ways. The first way is through a difference in phase offsets, represented by phi. So physically, this means that the waves initially started at different positions. Another way we can get phase difference is through a difference in distance traveled by the two waves. So x1 represents the distance traveled by the first wave, and x2 represents the distance traveled for the second wave. And so if the distance is such a way that the cosine becomes negative, well, this difference in distance is responsible for destructive interference. Now, remember that initially we assumed, based on the mathematical expression for the two waves, that we had the same angular frequency for both waves. But in reality, this might not be the case. And if we had, for example, omega 1 and omega 2, well, we would have had in the input of the cosine omega 1 minus omega 2. So phase difference and therefore interference can also occur from this difference in angular frequency. And the same applies, of course, for the spatial frequency. And so, in conclusion, the reason why intensities don't add up is because of this extra term that we have over here, which is responsible for wave interference.